All right, I think we'll get going. How's everybody doing?
Good.
Good?
How are you?
I'm good, thanks. How's homework going?
Haven't started.
Oh boy. Well, you're all grown adults. You know the consequences of your actions. Okay. How's that for like some parental whatever that is? You probably missed that a lot. Okay. So we're going to get going today. We're going to talk about how RNNs have been used in what has been called neural machine translation. So the hard task of translating from one language to another using computers. But when we say neural, of course, we're using neural networks. And RNNs were the state of the art for a while. And then, as I've said multiple times, they've really been replaced by transformers. But those come next week, so we'll spend some time learning a little bit about machine translation today and how RNNs were used to, set up kind of a new standard, and then some of the iterations that were made on top of those to make them even better. And in particular, one of the idea of attention, which is like the main mechanism in transformers, sort of gets like, I don't know if it was like the absolute first time it was used, but certainly it became very well known in this particular application of machine translation. And so it's sort of a precursor to what we found, what you see in transformers. Okay, so so we're going to start with some basic machine translation, and then we're going to get a little more advanced. That's where we'll find the attention. So this is, I will go through this really fast. This is what we've been talking about last two lectures, just how this works. Recurrent neural networks, they're meant to represent sequences. We have this nice linear structure with the nonlinear activation applied entry-wise, just in the same way that we learned in convolutional networks. Often, so in particular for neural machine translation, the idea of what we're doing here is that we're going to have two RNNs. We're going to have the one in blue, which we will think of as, we'll call it the encoder, and then we'll have the one in red that we'll think of as the decoder. One for one language, or for one language, one for the other. And again, the idea of encoding and decoding is that we're going to encode in this case, the English sentence into a vector or a sequence of vectors if we've got depth to our RNN, and then we will decode that into the new language. And this is a very common kind of language to use, especially in neural networks, is this idea of encoding data and then into like a vector representation and decoding it back to some more like recognizable data type. Oh yeah, I always do that, don't I? Like say it and it's in the slides. Okay, so remember I talked about this last time. There's some like special character that we introduced to let the network know that we're, like in this case, starting the translation to the new language, and then when it should finish as well. Because we can deal in this way, we can deal with variable length input and output. If we have a character that says, well, here's when we start and here's when we finish, and that's pretty useful. There's still, like when you actually write these things in code, they are going to have some fixed length. You can't just like it doesn't. you do have to sort of specify, like, we can't have a sequence longer than, you know, n tokens, but you pick something that's large enough, and everything works. Every sequence that you encode to, or you encode or decode, has to be within that length. We talked about this before as well. Oftentimes, you know, we have to have some way, our input, you know, we're given these tokens, we have some way of turning that into a vector representation to be able for it to be the input to a neural network. And there's a whole kind of class of things called word embeddings that are just ways of turning these words into these vectors. So the most naive way is to do a one-hot encoding. This will often be a bad choice if we have a large vocabulary, because we don't want to deal with vectors of, like, you know, length tens of thousands or even hundreds of thousands. So we often call those sparse embeddings, because it's, you know, like, everything's a 0 in that vector except for one entry that has a 1 to indicate, you know, like, I'm the word in this position in the vocabulary. I'm the ith word in the vocabulary. For word embeddings, you know, there's a number of ways to learn them that where the way that you're able to, so they are a much smaller dimension, usually in the low 100s of dimensions, and the way that works is that they're now dense vectors. So of course we couldn't have another sparse vector to represent tens of hundreds of thousands of tokens, you know, in a couple hundred dimensions. So they're now dense, and there's just, like, kind of like unsupervised ways of learning these that preserve that are learned in a way that kind of is meant to preserve some kind of, like, semantic meaning about the words and things like that. And there's lots of these. Like, the most famous are things like word2vec, or, like, there's another one that's probably more often used these days called glove. It's not the purpose of this course to go through what those are, but you can look them up, and you know, they're the kind of things that people found, and, you know, it was like you could add what are these words? It's like, you know, it's like man and, let's see, how does this work? You have, like, king and it needs the picture now. Like, king minus queen is, like, close to something like man, and, like, so, like, I don't know, you have these, like, you have these different kind of semantic meanings that are sort of, and it's kind of funny, like, we say it's equal to, but actually it's something like, it's one of the closest vectors, and these vectors have, like, angles that they're making in a space that are huge, like 40 or 50 degrees, but, so they're close, but they're not actually that close. But anyways, this has something to do with the supervision and how they're actually produced. But just know that, like, very often that's what's happening here. When we're thinking about these things, we are decoding, or we're first encoding these, we're embedding, as we call them, each of these tokens into a vector space, something of fixed length, usually in this low 100s. Okay, so again, just kind of recapping the flow, we have initial hidden states for each of the layers of our recurrent neural network. Usually those are set to 0, just as, like, some kind of standard practice, and then, you know, we forward the sequence through, updating the hidden state each time and passing that forward. And if we have multiple layers, then this whole thing kind of, you know, repeats. It's the only difference now is that instead of using the word embeddings for each of these tokens, we use the hidden state, or the output, the hidden state, the output from this cell as input to the next layer. So that's how you get layers in recurrent neural networks. And when we are decoding, we sort of follow a similar path. We decode, you know, the first layer, and then again, those hidden states that are produced here in the decoding, they're inputs to this next one, and then, you know, you can continue this process. You know, oftentimes, a lot of these will have depths of, like, you know, there'll be LSTMs with depth of, like, 4 or something like that, and that's often a pretty standard kind of architecture for doing these things. And it's from the last layer, that hidden state, that you then, you know, there's one more linear projection of that state to your scores in this, like, very high dimensional classification problem, right? Like, you're trying to, the way that these get supervised again is that you're trying to pick out the correct token in the vocabulary amongst all of the tokens in the vocabulary, right? And so if there's tens of thousands, there's going to be a classification problem where that softmax layer is going to have, dimension, whatever that is, tens of thousands. So it's a huge, it's a very high dimensional classification problem, but it can be done really, really well. It can be learned really well. Yeah, and then like the way this gets supervised again, right, is that we're trying to generate this sentence right here, and the idea is, what's the translation for this? Well, we're given pairs of these things, right? Like, I'm a student in English gets translated to je suis étudiant in French, and I don't speak French, so if that's wrong, sorry. But it's like what you're trying to get it to do is say if I'm just starting this translation, I need the first word to be je, and so you supervise it in that way, and then you feed je into the next one, saying what should be the next word in this translation. So given that I started and that the next word is je, I need to see suis here. So in that, so like these get supervised by the classification losses for each one of these, and they're also used as input to, in the sequence to generate the next one. So it's kind of got this nice kind of self-supervised feel to it that, once you have the data pairs, the translation pairs, that's all you need to train these things.
So this is really quite similar to captioning, right? Except that instead of using the image,
Yeah.
build up that starting point where you use that.
That's exactly right. So when we were doing captioning, the hidden state that you can think of the caption as a decoder of the image encoding. So we would feed the image encoding, as the initial hidden state into our decoder, and then it's done exactly the same way. It's exactly the same problem. Just we're conditioning this decoder in this case on the English sentence, and in the captioning case we're conditioning it on the encoding of the image. Right, we talked about this. Plain vanilla RNNs, they have a vanishing gradient problem. Oops, LSTMs, they have this kind of secondary track that doesn't have this kind of multiply many times by the same matrix problem. And so we don't get vanishing gradients. It was reminiscent of the skip connections in ResNets that also allows to have very very deep networks and train them effectively. So and then this is just this is sort of just doing what I just said. We would be computing the negative log likelihood. That's our loss of the correct term. That's the loss. We're going to add those all together, and we're going to jointly optimize this whole thing. So all those losses, and we backpropagate that. It says through time, but remember that just means kind of backwards through the sequence. Gradients are accumulated on at each step. Okay, training and test time. Remember this. This is at test time. Whatever the only difference is that whatever we produce here, when we are decoding the sentence, is going to be the word that shows up here. So if it's je, that's good because it's got a good chance of being decoded correctly. But if this ends up being some crazy word that's not je or whatever, it's some other French word, then we're going to be in a world of hurt because this is autoregressive in the sense that whatever happens here is going to be is going to affect what happens next. And so we hope that these things get started off correctly. So whatever, again, the way to think, the way that you do this is that you can either think of sampling this if you're going to be generating. Usually at test time though, you're going to test how you're doing, you're going to take after you apply your softmax, the word that has the highest likelihood, right, the largest probability, and that's what you're going to feed in. So in this case, this got decoded to moi. That's kind of close to je, it's just kind of the wrong, it's I versus me. So it's kind of you can see how something that was undertrained might do this because it's sort of got the idea that it's like a first person reference, but the wrong one. Blah, 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 blah. Okay, so sequence to sequence learning. So what we've been looking at is what we call sequence to sequence translation. So that idea of having an encoder and a decoder is known as sequence sequence or seek to seek is often is how you see it. SEQ, number 2 SEQ, and there, as it is right here. And this paper came out in 2014, so a couple years after the AlexNet paper. This now like breaks all kinds of records in being able to do machine translation between a variety of languages. And when it says deep LSTM here, this is precisely what I was saying. It's like the pictures we were just looking at. You have an LSTM, so you have the more complicated cells than just the plain vanilla. But then you're gonna have these are 4 layers deep, so you have 4 of those cell tracks lined up, and it's from the 4th one that that encoding that gets projected to become the scores for the decoding or the classification problem. Then there's like a variety of other types of things that were done around the same time. These ones were doing the best at that time. You can see things. You now know that there are things called LSTMs. There are things called GRUs. They're very similar to each other. This is quite interesting. Here's an approach where CNNs were used, so convolutional networks were used on the encoding, but an RNN, sort of this would end up being like an inverse CNN, was using the decoding. Anyways, so that was kind of like state of the art at first. Like the way that this gets evaluated is what's called a blue score. So that's an acronym for bilingual evaluation understudy, and it looks like this. This is the score. It's kind of a bizarre, tricky thing to look at, but the idea is the following. You have kind of 2 pieces to it. You have this brevity penalty times this exponential of whatever all this is here. So we look at this carefully. So you're trying to get higher scores are better in blue. So brevity penalty. So if the idea here is that we're trying to penalize very short translations. Like there's, the basic idea there is something like, usually those will be wrong, or they'll be too terse for them to be, accepted as like, I don't know, simple, just like I don't know, to be like natural language, to expect it to be kind of natural language translations. And so there's something where like if it's too short, this will be penalized. That value will be less than 1, and so there's some kind of penalty there. But more importantly is what comes after this thing right here. So what's happening here? You're looking at this thing that's called a modified precision. So modified precision is something where it's the way that this happens is it looks into what are called n-grams, and n-grams are pretty simple. They're just n is some number 1, 2, 3, 4. And they're just like subsequences of the words or the tokens in your sequence. So 1 gram is just like all the individual tokens, but a 2 gram would be like all the pairs of words or tokens in your sequence, and I should say sequential pairs. So not like like the first token and the 10th token, but 1 and 2, 2 and 3, 3 and 4, and so forth. Same thing for 3 grams, but it's going to be 1, 2 and 3, 2, 3 and 4, and so forth. N grams, 1 through n, 2 through n plus 1. And the idea is that like those are these n grams are you can compute the statistics of like how n grams appear, how often they appear, and like they appear near other n grams and things like that, and that somehow is a succinct way of capturing the statistics of your language. And so what this modified precision does is to look at your translations and to say something like, how many of the n-grams in my translation actually show up as n-grams in the correct translation. So instead of it being like we either get the whole sentence translated correctly or not, we actually are allowing for, we're trying to see if like all the 2 grams were somehow translated correctly, all the 3 grams, all the 4 grams, and you pick however many grams you want to go to. That's the capital N, n grams you want to go to, and then you kind of stop there. And it's weighted by the length of the n-gram. Anyways, the point is that this is a score that goes up if you do not suffer a penalty, or you have greater and greater matching n-grams at all the different levels, right? Each one of these is a log of a value between 0 and 1, and so these will be negative, from minus infinity to 0. So to maximize this, we want these to all be as close to 0 as possible, right? And the way that happens is that we get all of we find all of the n-grams in our translation. So with that as like basic understanding of what the blue score is about, here is in 2014, this was sort of like, this was the average and the state-of-the-art performance of SMT, so this is statistical machine translation, as opposed to NMT, neural machine translation. So this was non-neural network or deep learning type of approaches to machine translation. The state-of-the-art in 2014 got this blue score of 37. So this is now thought as a percent. The value was between 0 and 1. This is now scaled to be between 0 and 100. But anyways, so that was state-of-the-art, and then the average at that time amongst competing statistical machine translation systems was 33.3. When you bring in neural machine translation from that paper there, you don't get state-of-the-art performance just yet. You get this 34.8, and then if you combine some of the ideas of statistical machine translation with the neural machine translation, you get something almost state-of-the-art, but not quite. So in 2014, you all of a sudden had neural machine translations that were performing better than average, but not at state-of-the-art. And the notes that I'm trying to point out here is that oh, this took forever, but this was so fast. As somebody would say, I guess there's still value here even if it wasn't state-of-the-art. But really quickly, this was pushed to be state-of-the-art. By the way, this is just for English and French. There would be kind of there'd be different values here to compare against for any pair, any pair of languages, right? So English to German, or German to French, or whatever, right? Okay, so what changes? Well, before we get into what changes, what are the ways in which machine translation goes? This is just kind of a fun set of slides. Machine translation got a lot better than when I made these slides the first time. But yeah, there's you really want to get machine translation right, because the cost of certain failures is massive, right? A lot of these are just kind of goofy, right? Just kind of makes you kind of laugh, whatever. But there's some really high profile ones that happen, in the not too long ago past. Here's a classic one. So Benjamin Netanyahu was Prime Minister of Israel at the time. Netta, I forget her full name at this point, but it's a very famous performer, Israeli performer. He writes in Hebrew, some, I'm sure, very complimentary, post about, Netta, but it gets translated as, Netta, you're a real cow. And I'm sure there's some sort of idiomatic way of complimenting performers in Israeli that maybe had to do something with bovine characteristics or whatever, but this thing got translated in this way, and this is a pretty massive fail. Of course, you can just kind of blame it on the dumb translation system, but there's other more costly ones perhaps. this was this is a funny example. I don't, you can't, it's hard to, I don't read this language, but when I looked it up, these were a bunch of, I think they're like Finnish or something like that. I can't remember the name, but it's some sort of Scandinavian chefs. They made some order. They were using a translation system to make the order, and it's something like, instead of ordering like 15 dozen eggs or something like that, they ordered like 1,500 dozen eggs. So, something silly like this, but it had to do with like the machine translation. There's so many, if you just go looking around, there's just so many funny ones. Yeah. And then, I love this right here. So, I can't find it on Google, but it's delicious. And then, I really just love this one. Foreign candy always seems like the output of a slightly undertrained neural network. I don't know if you've spent, some of you are from foreign countries where they might have English names for foreign candies, but when you read these, like, these are pretty familiar if you've been to some parts of Europe or whatever, but like, these are weird things to say in English, like dairy milk, musk sticks, pineapple lumps, frogs alive. Like, these aren't really like, none of these actually sort of indicate that the thing you're going to eat when you open up this package is going to be good. All right, so 2014, you get this first kind of really great neural machine translation result. It's not state of the art amongst all machine translation systems, but it's getting pretty close. So, being very enterprising machine learning people, these groups went after, like how can we improve what we're doing? And the way that these systems really improved were, there are many ways in which they improve, but there's kind of three really interesting ones here that we're going to look at right now about like how to improve these things. So one has to do with dealing with vocabulary size. So remember, I keep saying that we're trying to do this like very high dimensional classification problem, choosing the correct word amongst like what could potentially be a very large vocabulary. So the larger that vocabulary becomes, like the more certain the model has to be around each like prediction, because so much probability can just be like diffusely, sort of like, I don't know, like uniformly scattered throughout the rest of the vocabulary, and then that can lead to just, with the vocabulary being so large, that will necessarily diminish the likelihood of the correct token, and so this becomes just like the resolution just it just becomes harder. So like, if there's something we can do about dealing with the vocabulary size, let's figure that out. So that's one of the problems we're going to go after. Like, how do we deal with large vocabulary sizes? The next one is sentence length. So turns out, and it sort of makes sense if you think about it, that the longer the sentence is, the harder it is to translate it. And the reason for that is that the longer it is, there's just the more dependencies there are within the sentence about like how it should be correctly translated. And while RNNs and LSTMs in particular are, built so that they can encode, all of the information that is in the sentence up to some point, there are limits, right? There are limits to the capacity of the models, and also just the ways that they were training them at the time, and like not all correlations can be jammed into like a single encoding vector. At least these models couldn't do that. So how do you deal with longer sentences? How do we translate those better? So that's number two, and then just language complexities. So like some languages share very similar grammars, very similar word lengths and things like this, and it makes it like very similar statistics for the languages, and so it makes it easier to translate between them. But if you're going to translate between like very different languages, the difference in the grammars, the difference in the complexity of the words, you think about like German words that can be so long because you're just like concatenating a bunch of nouns, like that can become very difficult for a system that's sort of based on tokenizing words in the vocabulary and then like understanding that compound grammar and things like that. So like, how can you deal with some of those things? So we'll go through each one of these. So what are the solutions? Just first is for vocabulary size, we're going to do this kind of really cool thing that's known as a copy mechanism. It's basically ignoring, like not translating rare words, and then more or less just like looking them up in a dictionary after we translate everything else, and usually that will work out just fine, it turns out. So that's pretty cool. Sentence length, this is where we get the attention mechanism. So if sentences get really long, you know, is there a way where we can allow, instead of just relying on the single hidden state at the point at which we're like decoding the, you know, the word in the sentence, can we allow the model to look back at the previous hidden states in some way and use those to now produce the current word in the phrase we're translating? And then language complexity, there's lots of ways you can do this. One of the ways, like the one way we're going to talk about is just having two levels of RNNs. One that's working at the word level, translating from, you know, like words to words, or phrases of words to words. But then for really difficult words that some, you know, again, like things that are rare or unknown, allowing there to be a character level RNN that will work, that will decode that particular token. And this really quickly gets us to very state-of-the-art performance. Yeah, so I've said this a million times. When we're going into, you know, when we were doing ImageNet, we had 1,000 categories, and that might have seemed like a lot, but actually that's like not very many. You know, if you think about vocabularies, especially if you think about like all the ways that you can like conjugate verbs and things like that, you have very, very, very large vocabularies. You know, tens of thousands, hundreds of thousands, millions of tokens. Like that, this becomes a very difficult classification problem. So the way that we deal with this is we say, okay, let's pick a size that we can sort of work with, and this becomes, you know, sometimes like a hyperparameter to the whole system. So let's pick a fixed size of our vocabulary that we're okay working with, in the sense that like we have confidence that we'll be able to do that classification problem just fine. And for everything else, what will that vocabulary look like? That'll be the vocabulary of the most frequent words we find in the language. So we can just like look at all of the, you know, the corpus of kind of like everything that you know, all the text that we have, like in this English to French translation. Just look at all of the if we're translating from French to English, all the French words, we can just like create a histogram of those. And for the words that like, you know, appear very frequently, like within the 50,000th or whatever that cutoff is, you know, they're the most frequent, then we keep them. Everything that's less frequent, we actually replace when we're doing the translation with just another token in the vocabulary that just says that we don't know what this is. Just like a placeholder that says a token is here, a word is here, but we're not going to try to translate it just yet. But know that it's there. And so that's the idea. You know, if you look at this kind of crazy sentence, if you know some French, then you know that, like, you know, these, well, this may be pretty obvious already. Like, these are proper names. These should not show up frequently in your vocabulary. We don't want to. We don't actually. If you think about it, there's really no need to translate a proper name. We usually just want to kind of copy that down, right? And then things that are rare often have, you know, a kind of funny look to them, in the sense that they, you know, like they're often just words that are very specific to, I don't know, a particular context, like in this case, like an economic context, or a financial context. And often, like, again, translation's pretty easy in the sense of, like, we can often just look these up. We can look them up in the dictionary and say, well, if that's, you know, whatever ecotax is in English, you know, we can look it up in French and it's ecotax, or how do you say that? So that's the idea. So we just have these placeholders, and they are still part of the translation. So, yeah, they're still part of the translation. So, sorry. Let me before I pass this on. So this So this was the paper, came out in 2015 that proposed this. The reason to maybe stop here is that this is like a who's who in deep learning on this paper. So they've all kind of gone different directions, but very, very, very like famous researchers in neural networks. Ilya, Kwok, and Oriol. We've talked about Ilya many times. He's the CSO over at OpenAI, and I think Kwok and Oriol are still at Google Research. Okay, so what do we try to do here? So we do the translation as always, but what we want to do is we want to have some kind of we want to be able to learn something about alignments, about how words from one grammar kind of get translated to another one. And so while we do have these unknowns, we sort of want to keep track of the order in which when we do the translation, we're gonna still translate unknown words, but to these unknown tokens. We want to keep track of which of the unknown tokens up here gets translated into which of the unknown tokens down here. And if we can keep track of that, then we can just do this kind of dictionary lookup. And so that's what we do. These get indicated. These get a kind of index to kind of keep track of that, and we just do the lookup in a dictionary. So maybe that kind of seems like cheating, but if you think about it, it's really smart, right? You're gonna use the neural networks to do what they do best, which is to understand the bulk statistics of the language and do the bulk of the translation. But we aren't going to force it. We're not going to at least at this time, we're not going to force this to learn very rare things. This actually requires a lot of capacity and a lot of training time, a lot of examples that we don't necessarily have in our training data. So do the translation, keep track of where the unknown tokens are, and then that's going to give us an ordering, and then just do a lookup and say, well, whatever ecotax is, give me the French word for that, and then if it's a proper name, then just directly translate the proper name, or directly copy down the proper name. And this becomes pretty. This is very effective. It turns out that if you remember, a blue score of 37 on the English to French translation problem was the state of the art of a statistical machine translation problem. This was the 2014 system, and then this one in 2015 gets a blue score of 37.5. Overall, this is showing how the blue scores at rarer and rarer, sentences with rarer and rarer words in them, and you can see that this is 0.5 blues, better. So this was state of the art, and of course, just like in deep learning, this becomes a new baseline, and everybody starts to try to do much better than that from there. So just that small change of going from translating everything to sort of only translating the most frequent words, and then doing this kind of dictionary lookup of the rest, all of a sudden gets a state of the art. So that's pretty cool, and it's a sort of a good story to remember in terms of how to use neural networks in machine learning in general as a tool. There's definitely a push, and rightly so from one perspective, to make your neural network do everything, do every single piece of everything in it. But it is one tool amongst many tools you could use to solve a problem, and usually the best solutions come by using the right tool for the right parts of the problem. And, that's the case here. Well, first, Chris.
Yeah. Are all unknown tokens treated the same? When you said that you track of the positions of each, is that just in code, or is that an actual embedding?
they get paired up. So you learn not only that, like, okay, so when you do the translation, like you're literally going to produce an unknown token, but you'll also produce a like pairing between them. So you learn that as well. Yeah. Okay. Cool. Yeah. So like that's what it's going to that's what it's going to do. So that you can take an unknown token from both and just know where to copy, the lookup from one to the other. By the way, do these blue scores, like, do they seem impressive or not? Like, was it at all intuitive how that was? Yeah, I know. Like, I mean, this isn't my area of like research, but like, I really have no intuition for this. I just know that larger is better. But like, what half a blue score is like, I don't really know. So, just admitting that I don't have a good feel for it, and if you don't have one, if you do have a good feel for it, tell me. I'd like to learn. But yeah. Okay, what kinds of translations do you get here? Like what sorts of things happen correctly? So here's some examples. This is the English phrase that we're trying to translate. Here is a human translation of it. Here is our machine translation of it with unknown tokens and then indexes kind of comparing or telling you which like words we should be connected to. And then here is the translation plus like the lookup of those pair of unknowns. And what's nice is you're getting numbers correctly. So notice that. So one thing I didn't say: these are words that are not in the bulk vocabulary. So numbers like 2600, pretty much all numbers except for very frequent numbers are not in this vocabulary. The words orthopedic and cataract, these are very specialized, right, in the medical some sense. So they're not in our bulk vocabulary. So there are things that are going to have to be looked up. So if you look at the translation, the number gets taken care of pretty easily, and then we get the correct French words in the places where we wanted them to go. Now, notice that this isn't like a perfect translation to the phrase, meaning like we didn't actually get back this exact phrase, but if you speak French well, I'm told that this actually means the same thing as this, or as the human the English original source phrase. So, anyways, works. You get proper names, even longer sentences, like because now you've made it, you've sort of reduced the burden of the of your RNN to only have to learn about like the bulk vocabulary, which is going to see a lot of examples of, and these unknown tokens. It actually allows it to translate longer sentences, not super long sentences, but it gets a bit better. And it's not perfect, obviously. Like that 37 is out of 100, so it's not like, or 37.5 is out of 100, so it's not like it's doing everything perfectly. In fact, in some sense, it doesn't. It seems like it has a long ways to go. But there are mistakes being made still as well. But better than the state of the art at the time. Okay, so we're going to move on to the next mechanism. Any questions on that? You get a basic understanding of like what's being done there, how the problem's solved. Yeah, go on.
Just to add to this vocabulary system, nowadays there is subword units instead of the road units. So if you have something like walking and going, so walk would be a token, go would be a token, ing would be the common. So you reduce the sparsity that way, so that the larger set of your vocabulary is covered, and you have a single output vocabulary or input vocabulary for multiple languages from the similar class of families. Like French and German may share some vocabulary, so you can have a single embedding there, something like that, and the input to reduce the sparsity of your subword.
So like stemming in some sense.
Yeah,
like
something like that.
Yeah. Okay.
To be very.
Yeah. Cool. Yeah. I don't know that if you could hear that or not. That Gernhoff was explaining that there are related kinds of ideas where another way to reduce the vocabulary is instead of having you know, all like the conjugations of verbs that you can stem those to like their, I don't know, like what that word would be called, like the primary form of the verb, and maybe keep track of like how it was. So you have that, and then you keep track of all of the ways in which it might have been conjugated, like the ing ending or something like the participle ending.
Basically, byte by byte. So you find out what is common and then pick it
Yeah,
up.
yeah. And so that reduces the vocabulary as well. Yeah. Thank you. That's great. Okay, so now sentence length. How do we deal with this? In some sense, it was dealt with the copy mechanism because we had a kind of a smaller vocabulary to deal with. But to get to much longer sentences, an idea was proposed by, I thought this was the next, yeah, okay. Anyways, an idea was proposed to allow, something that ended up being called attention, to allow the network to not just use the current encoding of everything that's come up beforehand, but to actually look back at the hidden states for all the states in the sequence beforehand, and somehow use those to create a combined embedding that might be better for decoding the word. And so, yeah, so this is meant to deal with the way that like translations really degrade when the sentences become long and really depend on so many long-range kind of correlations between different words. Yeah, there's this famous kind of researcher in natural language who, you see this often now that you kind of know about it, who has this saying that he became famous for, which is, you can't cram the meaning of a whole something sentence into a single something vector. So he was trying to say, like, all you crazy deep learning people, what are you doing? But then they said, I don't know, we're still going to use vectors. Here's a way we're going to do it, and they found a good solution. So I don't know if Ray's laughing or crying here, but his point is well taken in the sense that, you know, we could probably do better than just our single encoding of everything that's come before in the sentence or in the phrase, or, you know, the translated sentence, and then how much we translated to that, or translated to that point. So how does attention work? So the idea is, when we are going to decode, you know, the hidden state here, basically project it to the score so that we can do this classification problem. This is depending on the hidden state that's here, that's been built up out of all the hidden states before it in the first layer, that get to it, through all these arrows really. Then all the hidden states in the second layer, and through more layers and so forth. Right? They all are kind of getting aggregated to this single hidden state that then gets projected by a matrix to a vector of the right size for being the scores. And so the idea is something like, well, what if we just allowed, like before we took that hidden state and did that projection, what if we allowed the neural network to actually look at these previous hidden states and create a linear combination of all of them, the current hidden state and then those previous states from the encoder. And what if, what if we just allowed that, and what would happen? Is that somehow better? I don't know, if you think about it beforehand, if it's obvious it should be better or not, but that was the idea. It was like, okay, each of these hidden states here has something to do with the meaning of this sentence up to this point. So maybe having access to those and being able to create a linear combination from those, but in a learned way, meaning that we're going to learn the coefficients for how we do the linear combination. Maybe that will be better. Turns out it's it helps quite a bit, and became and it's now sort of like the primary mechanism that everybody sort of uses. I mean, it's been adapted quite a bit, and we'll talk about it next week. But this is sort of like the popular start of it. So what would this look like? Oh yeah, here are the people who published this paper in 2015. So notice what we have here. We have blue scores. I believe this is for, let's see. Well, maybe this is still English to French. I kind of forgot. But notice what we have here. We have a couple of different examples where the blue scores are going down for sentences that are much longer. And these are different versions of like the RNNs that we've been looking at. The point to see here is that the example with attention doesn't degrade as the sentence gets longer, at least up to 60 characters. And so all of a sudden, just allowing the network to be able to use these previous states, again, not cheating because they're it's information that we have access to just in these kind of interesting encoded way. By allowing that to happen, we now can translate sentences much better, even if they're very long. Yeah.
There's the 4 over on the side.
There's the what?
There's the 4.
Oh, the 4 different graphs. Yeah.
It looks like the solid line is the RNN search 50, and then there's the dotted line RNN search 50.
Right.
Does that one also have attention, or is it just your something else?
I can't. It has some kind of attention mechanism in it, but it's something different, and I can't remember quite what it is. I think the 30 and the 50 refer to something like how many states back in the encoder it's allowed to access. But honestly, I don't quite remember. Something like that. Okay, so what would this look like? All right, so we're trying to decode the next word in this translation, which should be sweet, right? Given this example over and over. And we wanted to use, up to this point, we've always been using just the hidden state as it's typically formed, from how we do RNNs. So, what do we do? Well, the thing that we're going to do differently is we are going to take the previous hidden state. Right? Remember, we're trying to create the current hidden state, so we don't have access to it. But we're going to take the previous hidden state, and we're going to compare it to the hidden states from each of the previous, or for each of the stages in the encoder. And we're going to have some way of comparing. So we're not going to say what that is. There's, we're going to, it could be any kind of way of measuring this, this kind of similarity, or just producing some kind of score to associate the two. This ends up, like in the simplest form, just being a dot product. So it really is about angular similarity, like how aligned these things are. But we're gonna compute that for each of those previous encoded states. Remember, like by the after we run these forward through the network, these are now fixed, right? So like these just for every stage of the decoding of the translation, these are just fixed vectors. And so whatever we have here, we're going to make this comparison. We just have simple numbers here, right? Like they produce some sort of score, 3, 5, 1, 1. And what we do is we're going to basically like apply a kind of softmax to them, so that these become normalized. So that you can think of it as like probabilities, but we're going to create a linear combination, and so this would be thought of as a convex combination of these things, all non-negative values that add to 1. So a convex combination of these previous states. And we're going to add those all together, right? So we're going to create a new vector, which is the linear combination, the convex combination of these vectors here with those weight vectors. So what comes out here depends on two things. Well, two sets of things. Whatever is this vector here, and then whatever these vectors are here, like the score that we compute for them. So if what comes out here will change depending on what these vectors are here or what this vector ends up being here. But we get this what we call a context vector, and then we combine that with our previous hidden state, and that gives us our current hidden state. So that's it. That's what the attention mechanism is. We are using this letter A here to, we think of these as like the attention coefficients, or the attention, just often just abbreviated, just called the attention. So Why do we call it attention? Is something like I think about, like, if you think of these as similarities, a little bit easier to talk about. If you think of these as similarities, we're trying to create a new vector out of these vectors, and the larger this coefficient is, the more we're like paying attention to it and creating this context vector. So that's why it's called attention, and you know, like, who's paying attention? Well, it's like this thing over here is paying attention, I guess. You know, but that's why it's called attention. We're somehow saying, you know, letting this thing say, how much should we pay attention to each one of these vectors and creating a context vector to then combine with the hidden state and become previous hidden state and become a new hidden state. Yeah.
So attention is learned, correct?
Yeah, so it's learned. So we're going to back propagate through this operation.
So would it, I guess I'm kind of confused how that changes for different sized sentences, because like you'd have to know how long the sentence is going to be, right? And you start putting the attention.
Well, no, I mean, like, you can do this. You can do this for, you know, any variable length sentence, right? Like, you can create the coefficients, whether this is like two words or this is 20 words.
So you create it after you've done.
Yeah. So I first forward my sentence, whether it's got 4 tokens or 40 or whatever.
Sure.
I forward them through, and if it's 4, there's going to be 4 vectors that I'm going to be creating attention coefficients for. But if there's 40, I'm going to create 40 attention coefficients.
But I only create them after I've reached the end of my sentence.
Yes. Yeah. Exactly.
So
Okay. So we only do this in the decoding. We don't do this in the encoding.
Okay.
So the encoder, we don't do this attention mechanism. Only when we're in the decoder decoding the hidden states to the correct word.
Okay. Thank you.
Yeah. Good question. So, yeah, and it's learned. This is really important. So this operation of, like, whatever that score function is, needs to be a differentiable operation that we, you know, it could have parameters or it couldn't. But this does create dependencies, new dependencies in the computation graph for when we decode this word, that loss there now not only gets back propagated along, you know, all these, you know, going backwards over these arrows, but will now go through like this arrow and these arrows as well, in terms of, you know, creating additional signal. Yeah. So I don't know that it's obvious that this should help, you know, at all, but in another way of thinking about it, like, it kind of has to help, because what this is doing is just adding more information to what we already had, right? Like, it's giving it access to all of these states, these hidden states in the encoder, and allowing, in a learned way, to combine them so that, you know, we can do a better job at this objective of getting the right word. So like, yes, it should be better, because you know, like, in an information theoretic way, like, there's just more information accessible to this one here, but I don't know, it maybe seems kind of weird or complex. But it ends up working great, as you saw in that particular example. Once this was out, there were lots of different uses of it and versions of it, and like, there's another paper that allowed this, like, which vectors you actually, you know, use to be learned as well. So not just combining all of them, but, you know, picking out subsets of the source. But anyways, these things started giving state-of-the-art machine translation, you know, not only for English and French, but a whole bunch of different languages. This was one for English to German. Again, another really famous name in machine learning, Chris Manning. And, you know, we can do much, much better at longer sentences as a result. So that's the key there. What is this? What do we pick up from this? Well, I mean, maybe a lot of things, but in particular, this seems to do a really good job of being able to learn some of the more complex forms, like parts of certain grammars, like double negation. If you think about this is quite a difficult problem, even just for people learning to speak the language, right? Like, you're trying to keep state of, like, every time I negate something, I need to know that I've negated it one more time to know what the negation state is, right? So if you think about it, attention is actually really great for this because it's allowing, using whatever score function you're using, adjusted in such a way that it can learn to do these more complicated things, just simply because they have access to it. So here's an example of that working. Notice that we still have like the unknowns in here. So like this was, once the copy mechanism was known, like everybody started using it. So like that's being used here. This is 2015 and beyond. But you see, it gets the double negative correct. Yeah, that's one of that's a great example of something that it does really well. And again, it's going to be the basis of like everything that we have, all like the transformers and all the versions of transformers that are out there these days. Okay, the final thing here is just language complexity. Things can get really complex at the word level. Things about like very different alphabets can be really complex. Like these things about languages that allow you to put a whole bunch of words together and not become a new word in the vocabulary. So something like an open vocabulary or informal spellings or things like that. Like we want to be able to do well on even these kinds of difficult aspects of translation, right? So like, solar system, it's 2 words in one language, it's a single word in another one, whatever this crazy thing is here. So how do we do that? The mechanism is this, is that we just have this sort of, we have a recurrent neural network within a recurrent neural network. So the idea is simply, we've got unknowns, as before, and sometimes these unknowns are going to be unknowns that we're going to want to try to translate at a character level. And literally, you just take the words that should be paired up, through the unknown pairing mechanism, and then you make an attempt at doing the character level decoding. So, a cute cat, un joli chat, I don't know how you say it right, but we've just sort of like recursed in one level at the word level and said, okay, let's attempt to translate this at the character level and see if we can do any better. And we do. What's kind of cool about this is that it does deal with it does deal with like some of these really difficult kind of like word morphology problems, like these and these. And as long as you have like the right pairing of these words, it can learn to and enough of these examples, it can learn to sort of deal with these, like in the sense of, if we need to put these together, like it can learn to say, okay, well, I know I should make, like things like this should be concatenated, and I know I can break these kinds of things up and so forth. So, yeah.
Does this replace the dictionary lookup?
It doesn't replace it. It gets used. I kind of forget the mechanism right now, but it gets used when there's like there's some kind of trigger for it besides just the copy mechanism, and honestly I'm forgetting what it is right now. I'll remind myself, and I'll come back next time, or just post it on Canvas. I kind of forget what it is. There's some kind of trigger for when you want to do it. So it's like you only go to the character level when needed, whatever that needed is. I can't remember. There's like some kind of confidence in like your ability to look it up. It's like something maybe really simple. I just can't remember. It's like, is it in the dictionary or not?
Yeah, I think that's more or less the answer to my question.
Yeah. Okay. If it's in the dictionary, then just do it. If not, we're going to rely on something crazy like this. Okay. So. Yeah, I mean, it does, again, require there being good training data to be able to do this, but, like most deep learning systems, as long as you've got enough of the right kind of data, you can usually learn to do these things fairly well. And if you think about this, I don't know a whole lot about the Czech language, but I know I have been there a couple times, and I know it looks crazy to me at least. You know, like somewhat different alphabet, and you know, grammar certainly is very, very different. So this is a much harder problem than say like an English to French translation. But you can see that. Okay, so like this is some sort of like standard at the word level neural machine translation. It performs at this level. The character base performs at this level. It's better. The single model is better, but it's super slow. You think about that, just like and just like the dependencies in that. But if you now do this hybrid where you have the two plus like the copy mechanism, then you get this 19.6, which is much better than any of the other translations at this time. And by 2015, no one's comparing anymore to statistical machine translation systems. They're just no one's working on them anymore. Like they can't be improved faster than the improvements that are coming here. And so everybody's in these areas are sort of working on neural networks at this point. And as always, you ensemble some models together that you can usually eke out a little better performance. Okay, so that's that. And we actually finished again with 10 minutes to go. Any questions before we sort of drop out of that? Yeah.
About the blue score.
Yeah.
So you were saying it's like sequence of optical.
Yeah, the n-grams.
Yeah. And was that the one language to another? Or?
Yeah. One language to another. So it's like you have n-grams in one, n-grams in the other.
How
And
exactly is that? Is it just like generally like?
well, it's not a loss function. It's just like a way of like saying, okay, I have my source sentence, I have my translation. I can compute. Sorry, I have my source sentence, I have like my human translations, and I have my machine translation. So I can look at n-grams within my machine translation, I can look at my n-grams within my human translation, and I'm comparing those.
Okay, so it's of the same translated language, not.
Yeah, oh yeah, definitely. Otherwise it wouldn't make any sense.
Right.
Yeah.
Absolutely.
Makes sense why it wasn't making sense. Cool. So that's that for neural machine translation. We'll talk about transformers next time, and you'll be introduced to kind of the state of the art in these areas. I'll hang out here if you got questions. Otherwise,